Hello all, welcome back to Electronic Device and Circuits video lecture series. I am BV Satyanarayana, Associate Professor in Department of ECE, Vision Institute of Technology, Bhimavaram. In unit number 3, rectifiers and filters, we already discussed about introduction to RPS, basic rectifier setup, off-wave rectifier operation and waveforms, center tapped full wave rectifier operation and waveforms, bridge rectifier operation and waveforms, and off-wave rectifier characteristics such as average DC load current, average DC load voltage, RMS value of load current. Now, in this video, I am trying to derive the expression for DC output power, AC input power, rectifier efficiency of off-wave rectifier. The objectives of this lecture are derivation for DC output power, derivation for AC input power, derivation for rectifier efficiency. In the last lecture, we already derived three expressions for the off-wave rectifier characteristics. Now, the fourth characteristic is DC power output, PDC. We know that P equal to VI, P equal to VI. Here I want PDC, so PDC equal to VDC into IDC. That is power in terms of voltage and current. So this PDC is also equal to VDC equal to IDC into RL multiplied by IDC, which is equal to PDC equal to IDC square into RL. So this is one expression for output DC power. And we also know that IDC equal to VDC by RL. So our PDC, it becomes VDC by RL whole square into RL, which is equal to VDC square by RL. So that is the output power, DC output power in terms of voltage, VDC. Consider PDC equal to IDC square into RL, and we know that IDC equal to Im by pi, where Im is the peak value of the load current. Then the PDC becomes Im by pi whole square into RL. That is also equal to Im square RL by pi square. So that is PDC in terms of Im. So we can express this PDC in terms of Vm also. So we know that Im equal to Vm by Rs plus Rf plus RL. Substitute this in the above expression, then we are getting PDC as PDC equal to . Vm square RL by pi square into Rs plus Rf plus RL whole square. So that is PDC in terms of Vm. So all these are the expressions for DC output power of Wave Rectifier. Then I'm trying to calculate AC input power supplied to Wave Rectifier. The power input taken from the secondary of the transformer is supplied to three resistances, that is Rs, Rf and RL. RL is the secondary winding resistance, Rf is the diode forward resistance, and RL is the load resistance. So if you draw the equivalent circuit of the secondary, it is the secondary winding, the internal resistance is Rs, diode forward resistance is Rf, and the load resistance RL. So now I'm trying to calculate the AC power. So I already told AC values in general expressed in RMS. That's why I'm assuming the current flowing in this circuit is IRMS. IRMS. Now our AC input power PAC is equal to I square R. I square R. Here R I am calling it as a R equivalent. So I it is IRMS. So that gives the AC power supplied to the off-wave rectifier. So this PAC is equal to IRMS square into R equivalent. What is the R equivalent? RS, RF, RL are in series. So R equivalent equal to RS plus RF plus RL. And we know that for off-wave rectifier, IRMS equal to Im by 2. Substitute this in the above expression, then PAC equal to Im by 2 whole square into Rs plus Rf plus RL. So the AC input power supplied is equal to Im square by 4 into Rs plus Rf plus RL. So this is the input power supplied. Then the next characteristic of off-wave rectifier is rectifier efficiency. The rectifier efficiency is defined as the ratio of DC power output to AC input power. So the efficiency is equal to DC output power by AC input power supplied. So in general efficiency it is expressed in percentage. So multiplied by 100. So the efficiency is equal to PDC by PAC into 100. So we already calculated PDC and PAC. If you divide those two expressions, then we are getting the expression for efficiency. So here I'm assuming PDC in terms of Im, which is equal to Im square by pi square into RL divided with PAC in terms of I am assuming, so it is Im square by 4 into RS plus RF plus RL. So here this Im square and Im square, it is cancelled out. So the efficiency is equal to 4 by pi square into RL by RS plus RF plus RL. Then the efficiency is equal to 4 by pi square is equal to 0.406 divided with, so RS plus RF by RL plus 1. Yeah, here RS and RF are internal resistances. Those are very small compared to RL. So we can neglect those two values. Then the efficiency percentile is equal to 40.6. The efficiency of off-wave rectifier is 40.6. Okay. So here efficiency means PDC by PAC equal to 40.6, means PDC equal to 40.6 into PAC, means in off-wave rectifier maximum 40.6 percentile of AC power gets converted to DC power in the load, and the remaining 60%, it appears in the output as ripples, means which is the fluctuating component. Only 40.6 percentile of AC input power is converted to DC, and the remaining 60% will appear as a ripple content, means the fluctuating content. Thus, more the efficiency, less or the ripple content in the output. For a rectifier, the efficiency should be as high as possible. If the efficiency is 100%, means all the AC input power is converted to DC output power. Otherwise, there are some AC component present in the output. And coming to the summary, in this lecture, we have learnt the following: derivation for DC output power, derivation for AC input power, derivation for rectifier efficiency. In the next lecture, I will try to derive the expressions for ripple factor, peak inverse voltage, and transformer utilization factor. Thank you. Thank you all.